Welcome to the deep dive. Ever wonder how scientists actually predict the sun's, well, its mood swings, and why we should even care?
Right, because it affects things down here. Satellites, our communication systems. A grumpy sun can cause real problems.
Exactly. So today we're looking at a different approach some researchers are taking using machine learning, not just the usual statistical methods or deep learning, to forecast solar activity.
Yeah, it's a fascinating angle. Our mission basically is to get a handle on what these ML models predict for the next couple of solar cycles. That's 25 and 26.
And they're basing this on some serious data, right?
Yeah, they've crunched 149 years of monthly sunspot area data. Goes way back May 1874 up to April 2023.
Wow, 149 years. That's quite a data set. And you mentioned machine learning models. Which ones are we talking about?
So they used a suite of them, things like ridge regression, XGBoost, random forest like GBM, and CatBoost too.
Okay, that sounds pretty techy. Ensemble methods, you called them?
That's the idea. Instead of relying on one model, you combine several. It's like getting a second, third, fourth opinion often leads to a more, robust prediction.
Makes sense. And this sunspot area data, it comes from Belgium.
That's right. WDC Silso, Royal Observatory of Belgium. They measure the sunspot area in millions of the solar hemisphere. That's the key metric here.
Got it. But how do they even know this long-term data is, well, predictable? Isn't solar activity kind of chaotic?
That's a fair question. They actually checked that first. They used something called the Augmented Dickey-Fuller Test, ADF test, to see if the data was stationary.
Stationary?
Meaning it has consistent statistical properties over time, like a stable mean and variance, not just random noise. It passed the test. So, good news for forecasting.
Okay, so the data's solid.
Yeah.
And they split it, right? Train the models on the past.
Exactly. A time-based split. You train on, say, the first 80% of the data and test how well the model predicts the remaining 20%. Standard practice.
And how does the model actually learn to predict? What does it look at?
They used a sort of sliding window approach. They fed the models sequences of the last 96 monthly sunspot values.
That's 8 years' worth.
Right. 8 years of history to predict the value for the very next month.
All right, let's get to the predictions. Solar cycle 25, the one happening now, what's the forecast?
Well, the general consensus from these models is that cycle 25 will likely be weaker than the last two, cycles 23 and 24.
Weaker, okay. Any specifics on the peak?
Yeah, there's some variation, which you'd expect. Random Forest predicts the highest peak, around 1704 microhemispheres, peaking in June 2024.
June 2024, what about the others?
XGBoost and LightGBM are pretty close. They predict peaks around 1543 and 1562, respectively, both pointing to April 2024.
April, so a bit earlier.
A little bit. Then you have ridge regression, a bit lower at 1354 in May 2024, and CatBoost at about 1467, also in April 2024.
So it sounds like most models are clustering around April to June 2024 for the peak time.
Exactly. And the peak strength seems to be hovering around, say, 1500 plus or minus 200 microhemispheres. That's the ballpark.
And did any models perform better for this cycle?
Based on the testing metrics, they reported things like RMSE, R squared, MAPE. Random Forest and LightGBM look particularly strong for cycle 25.
Okay, interesting. Now looking further ahead, solar cycle 26, what does the machine learning crystal ball say about that?
Well, here things get a bit more spread out. The predictions diverge more.
How so?
Random Forest predicts a peak around 975, way out in July 2037. XGBoost is similar, maybe slightly lower at 910, around June 2037.
So quite a bit weaker peaks for those two and further out?
Yeah, but then LightGBM throws a curveball. It predicts a much stronger peak, almost 1600, 1586 specifically, and much earlier, June 2035.
Whoa, that's a big difference. June 2035 versus mid-2037, and almost double the peak strength.
Exactly. And CatBoost is closer to the Random Forest XGBoost prediction and strength, around 960, but peaks earlier, September 2034.
So the timing for cycle 26 is really quite uncertain according to these models.
Very much so. Even though Random Forest and XGBoost showed good performance metrics again for cycle 26, this divergence, especially with LightGBM, shows the challenge of forecasting that far ahead.
It really highlights the uncertainty. How do these cycle 25 predictions stack up against other recent studies? Are they in the same ballpark?
Good question. Comparing them provides context. Other studies published in the last few years have shown quite a range for cycle 25's peak. Some predicted much lower peaks, maybe around 1100. Others went way higher, even over 2500.
Wow, that's a huge range.
It is, and the timing varied too. So this study's results, predicting a peak around 1500 in mid-2024, sort of fit within that broader spectrum, maybe leaning towards a moderate to weaker cycle compared to some really high predictions.
Okay, so it adds another data point, reinforcing that it's complex.
Precisely. It underscores that solar cycle prediction is still an active area of research with ongoing debate.
So wrapping this up, what's the key takeaway from this machine learning approach to solar forecasting?
I think the main point is that these ensemble machine learning methods are genuinely useful tools. They offer valuable insights. For cycle 25, the weight of this evidence points towards a relatively weaker cycle, peaking around the middle of 2024.
But for cycle 26,
Hmm.
more question marks.
Definitely. The predictions are much less consistent, especially the timing. It signals that predicting further out is still quite tricky, and there's work to be done to improve the model's long-range reliability.
And I assume the researchers are digging into why light GBM, for instance, gave such a different result for cycle 26.
Absolutely. Understanding those differences between well-performing models is crucial for improving future forecasts. It's an ongoing process.
Right. So thinking about this, even a weaker cycle 25 still has implications for our technology, our power grids, satellites. It makes you think, doesn't it? What specific areas of our lives might be most vulnerable to these solar fluctuations in the coming decade?
That's the critical question to ponder. As we rely more and more on technology, understanding space weather becomes increasingly important. Food for thought indeed.
Definitely something to keep an eye on. Thanks for diving into the sun's future with us today. Join us next time for another deep dive.